Insulating material. Introduction. Solid, liquid, and gaseous insulations have been used in the electrical industry for different apparatus. They form one of the most important components in all electrical apparatus, including busbar systems. Porcelain, and glass to a limited extent, has been used as an insulator for indoor and outdoor applications ever since the commercialization of electric power. Disc insulators made of glass have been used in transmission lines. Oil has been extensively used in transformers and continues to be the prime insulation medium in power and distribution transformers and high-voltage instrument transformers. Oil had also been used in bulk and minimum oil circuit breakers for providing insulation and efficient quenching of the arc. Oil is still used as an insulating medium in oil-filled cables. Considerable research in the field over the past century in organic insulation has resulted in the development of synthetic resins, epoxy, polyester, cycloaliphatic, polyurethane, that had the desired properties. Glass-reinforced resin components such as dough molding compound, sheet molding compounds, pultrusions, and filament wound components were developed. Composite insulators are replacing them increasingly in outdoor applications as in post insulators, housings of switchyard equipment, and transmission line insulation. Films and tapes were developed to meet the ever-increasing demand for better thermal and dielectric properties in the transformer and motor industries. These have now been adopted in the switchgear and busbar systems industry as well. Developments in vacuum and sulfur hexafluoride technologies had led to their use in switchgear. Vacuum bottles are used in medium voltage circuit breakers in distribution and generator connections. Both are now used as insulating and arc quenching media in gas-insulated bus. Alternatives to sulfur hexafluoride are being looked into, as it has been identified as a greenhouse gas in the Kyoto Protocol. A gas mixture of 20% sulfur hexafluoride and 80% nitrogen, considered to be less harmful to the environment and also cost-effective, is now being used in a gas-insulated bus. Minnesota Mining and Manufacturing, 3M, US have developed green gas for grid, G3, which is not a greenhouse gas, and has been successfully used in gas-insulated bus in commercial operation. The minimum thermal class of insulation in busbar systems should be Class B, so that it meets the general requirements of international standards. A majority of all failures in a busbar system can be traced back to the failure of the insulator or the insulating medium. Insulator cost is a significant part of the overall cost of the busbar system. The insulating material in busbar systems can be broadly classified as under: porcelain and glass, synthetic resin with or without glass, polyester films, insulating gas. The following major properties are to be considered when selecting an insulation system. Electrical properties. Good electrical properties are the most important criteria for insulating material. Among others, these include high breakdown voltage, low loss angle, tan delta, and high surface resistivity. Mechanical properties. Good mechanical properties of insulating material will result in a compact insulator. Among others, these include a combination of high tensile, compression, cantilever, torsional, cross-breaking and impact strength, and moldability. Corrosion and ultraviolet resistance. Insulating material must be suitable to withstand the ambient atmosphere, which may be corrosive. Insulators exposed to the atmosphere must also have resistance to ultraviolet radiation. Most insulators have metal parts embedded at either end for connections. While the insulating material is susceptible to degradation due to ultraviolet radiation and corrosion, the embedded inserts and metal parts are susceptible to corrosion. Thermal class. The thermal class of insulation must meet the requirements of the envisaged temperature of the conductor during operating conditions. For most busbar systems conforming to international specifications, Class B insulation will meet the requirements. Selecting a higher class of insulation, believing it to provide a higher safety margin, does not improve the life or performance of the product, and only serves to increase the cost. Expected life, organic insulations. An insulator made of organic material will decay and has a definite life. The life of organic insulating material is around 20 to 25 years. Any thermal overload reduces its life. Arrhenius law. It is generally accepted that an increase of the operating temperature of 8 to 10 degrees Celsius over the rated value reduces the service life by 50%. Similarly, an insulation system is designed for an operating voltage. If organic insulation is subjected to continuous, repeated power frequency overvoltage or surges, it could impact its life significantly and can lead to failure. It is generally accepted that an increase in the operating voltage by 8 to 10% over the rated voltage reduces the service life by 50%. Porcelain. Porcelain insulators and bushings have been used in the electrical industry since its inception. They have excellent dielectric properties, long life, are resistant to atmospheric corrosion and ultraviolet radiation. The infrastructure cost to manufacture porcelain component is very heavy. The process is extremely labor-intensive and requires very skilled engineering and operating staff. The dielectric properties of a porcelain insulator, in most cases, can be fully restored, after a flashover across its surface, by washing with solvent and water and cleaning the same. Porcelain insulators have excellent resistance to water absorption. The porcelain manufacturing process, in brief, comprises raw material, slip house, pugging, jigging, finishing, sandering and glazing, firing, metallics, assembly, testing. Glass. Disc insulators made of glass have been used in transmission lines for the past few decades. These have not been installed as bus support insulators either in an open bus or metal enclosed bus. The reason for it becomes evident when one understands the manufacturing process. One of the advantages of glass insulators is that, unlike porcelain, any component rejected due to defects or shattering while processing can be recycled. It is, therefore, environmentally friendly. One of the major disadvantages of glass insulators is that moisture can easily condense on the surface. This can facilitate the deposition of dust, leading to increased leakage current. Glass insulators can be coated to improve its surface properties. Glass insulators are cheaper than porcelain insulators. Resin. Porcelain insulators have to be manufactured in bulk for a commercially viable price and require a long lead time dictated by the process. With the porcelain insulators and bushings getting expensive and requiring longer lead time, they began to get substituted gradually by synthetic resin insulators and bushings. Due to their low cost, lightweight, better lead time, and acceptable mechanical and electrical properties, several manufacturers of busbar systems have opted for insulators and bushings manufactured with synthetic resins. Synthetic resins can be formulated and synthesized to deliver the desired performance for a given application. Common terminologies associated with the resin manufacturing and processing industry are listed below. Fillers are added to the resin. Pigment pastes, that are predominantly inorganic, are added to the mix. Catalysts, initiators, activators are added to the resin in a one-part system to commence the process of polymerization. Hardener is a part of a two-part system to react with resin for chemical bonding. Accelerator is added to the resin mix to accelerate the reaction. Glass transition temperature, GTT, on when tested under controlled conditions, under mechanical load, as defined by the standards. Plasticizer is added to the resin mix to predominantly give adequate flexibility. Pot life is the time taken for viscosity to double from the time the product is mixed and is measured at room temperature. Working life is the time a resin retains low enough viscosity that it can be used for a specific application. Gel time is the time interval between the introduction of the catalyst and the formation of a gel. Exothermic reaction is a chemical reaction that results in the liberation of heat. Thermoset materials are those products that undergo a permanent transformation at a threshold elevated temperature. Curing is the process of cross-linking and attaining the desired parameters after the process has been initiated. Potting or encapsulation is a process of providing a protective cover to offer protection against moisture, water, and a corrosive atmosphere. It can also be used for electrical insulation and protection against ultraviolet radiation. Impregnation is a process by which a reinforcement or filler is completely encapsulated. Resin reaction. Synthetic resins are commercially available in solid and liquid forms. The resin products are manufactured for a one-component system or a two-component system. One-component system. In the one-component system, normally with polyester resin, resin mixed with the initiator in the desired proportion is packaged in a common container. The component needs to be heated to a specific temperature to initiate a reaction for bonding and kept for a specific duration for it to attain the mechanical properties. Two-component system. In the two-component system, normally with epoxy resin, the resin and the hardener are mixed to trigger polymerization. This process is associated with an exothermic reaction resulting in cross-linking. Resin classification. For the busbar systems, the resin components are classified based on the raw material and process. Each of them has specific application and cost implications. Epoxy resin. Epoxy resin with glass reinforcement. Polyester resin. Polyester resin with glass reinforcement. Polyurethane resin. Cycloaliphatic resin. Composites. Epoxy resin. The process of making an epoxy resin cast component is comparatively simple. Epoxy resin and filler, of correct sieve, are thoroughly mixed in the recommended proportions. The filler is either quartz or alumina. The mix is heated to a slightly elevated temperature and stirred continuously to avoid settling of filler. Hardener and plasticizer are added to the mix in the desired ratio and stirred. Accelerators are added in the right proportion before pouring into the molds. This is an exothermic reaction. The mixing chamber is desired to be kept under vacuum for optimum mix quantity that is void and moisture-free. The process is also referred to as degassing. In one process, the mold is preheated and placed inside a vacuum chamber. The mix is then poured under vacuum into the mold very slowly, by gravity. Once the mold is filled, further heat is applied to complete the curing. The component is demolded after complete curing is achieved. It should be noted that the mix will shrink inside the mold during the cooling process, and therefore, the mold design should cater to the same. Alternatively, the mix is injected into the heated mold under pressure. The injection pressure must be maintained in the injection line so that any curing shrinkage can be compensated for by the resin being pushed into the mold. The mold is taken out and the product is released after a defined time. Glass reinforced epoxy resin. Glass has been used as a reinforcing agent in epoxy resin components to significantly improve mechanical strength. Depending upon the shape of the component, the mechanical strength of the epoxy can be enhanced several times by reinforcing it with glass. There are various methods of reinforcements, depending upon the shape, size, and application of the product. Hollow cylindrical or conical components can be made by filament winding. Filament wound cylinders are used as housings for the composite insulators, transformers, bushings, outdoor instrument transformers, and lightning arresters. High-strength, long, profiled insulating components are manufactured by a process called pultrusions. The process comprises a large number of glass filaments, passing through a mix of epoxy resin and hardener and converging to a profiled mold and pulled at the other end. Glass-reinforced epoxy resin components are used in busbar systems as support blocks, bushings, phase barriers, and tie rods. Polyester resin. Polyester resin is commercially available in liquid form. It normally has a shelf life of about 1 year, and it is advisable to use the same within 6 months of the date of manufacture. Polymerization of polyester resin can be initiated by a catalyst, methyl ethyl ketone peroxide, MEKP, that is mixed in a specified proportion. A filler can be added to the resin as per the desired ratio to deliver the specified parameters. The filler should be heated to remove moisture and stored in sealed packets. The filler should be thoroughly mixed with the resin before mixing the catalyst. Polyester resin is used for the encapsulation and insulation of components. There are various grades of commercially available polyester resins such as orthophthalic resin, terephthalic resin, and isophthalic resin, which can be used depending on the end properties of the product and the costs. Glass-reinforced polyester resin. Glass-reinforced polyester resins are used in the electrical industry for low-voltage applications such as laminated sheets, insulators, bushings, and a large variety of components. Filament winding of cylinders, pultrusions, and glass-reinforced sheets can be manufactured with polyester resin by the same process as that carried out for the epoxy resin. In general, polyester resins are less viscous compared to epoxy resin. Further, glass-mixed polyester resins with pigments, fillers, and catalysts are readily available from the manufacturers of the resins. These are available in 2 specific glass compositions and are used, depending upon the shape of the component, to be molded. 1-part resin, dough-molded compound, DMC, and sheet-molded compound, SMC, have been extensively used as insulators for low-voltage applications. The type of compound, DMC or SMC, to be molded depends upon the shape of the component. Polyurethane resin. Polyurethane has not found much acceptance in busbar systems application, unlike in the building industry where polyurethane foam has been universally accepted as thermal insulation. It is used as a coating and bonding material for a variety of applications. It is used as a potting, encapsulating compound for low and medium voltage instrument transformers, varnish for improving anti-tracking properties, coat paint for protection against corrosive atmosphere. Polyurethane resin for potting is commercially available in a liquid state, pre-mixed with a filler element that is quartz or silica. Formulations are available in a two-part process system. The properties of the polyurethane are very similar to that of epoxy resin. It is tough and has better impact resistance. The thermal class of insulation is low and hence, its application is limited. Cycloaliphatic resin. Cycloaliphatic epoxy resins are non-aromatic and have fully saturated molecular structures. They are suited for use in applications requiring resistance to ultraviolet degradation, outdoor application, and electrical arc tracking. Cycloaliphatic resins are also ideally suited for applications in severe environments such as near sea coasts and areas of high industrial pollution. Among their most notable features are their inherently low viscosity, coupled with excellent weathering and electrical performance. The inherent low viscosity of these resins enables them to be formulated with higher levels of inorganic fillers like quartz or silica. This enhances mechanical properties and electrical track resistance for such components. Pultrusion can be synthesized and manufactured to meet any product and project specifications. Its mechanical and electrical properties can be customized. Since these are pulled through a die of desired configuration, it does not undergo further mechanical operations. They are cut to length and assembled. Filament wound cylinders can be synthesized to meet any product and project specifications. Its mechanical and electrical properties can be customized. Filament wound tubes are invariably machined to the desired dimensions to tolerances for assembly into a sub-assembly. Pultruded sections and filament wound tubes can be synthesized and manufactured to suit the product-specific requirements. Composites. Composite insulations have found usage in outdoor installations. A composite insulator comprises a glass-reinforced core, covered with a silicone rubber casing. The glass-reinforced core provides the necessary insulation and mechanical strength, while the covering protects against ultraviolet radiations and atmospheric pollutants. The covering can be profiled for desired creepage distance. The core can be a pultruded rod of glass epoxy as in the case of transmission lines, string insulators, or can be a filament wound cylinder as in the case of post insulators in switch yards. Housings of high-voltage oil-immersed current transformers and voltage transformers also use composite insulation. The filament wound cylinder diameter can be profiled from top to bottom for optimal design. Lightning arrestor housings are also made of composites since filament wound tubes can withstand very high pressures and do not shatter when absorbing the energy of an electrical surge. Shattering of lightning arrestor housing can damage expensive switchyard equipment in the vicinity of its installation. Metal parts or flanges, normally made of spheroidal grey iron, can be glued and attached as per the application requirements. The core can be inserted into a silicone rubber skirt of the desired profile to provide the necessary creepage. Composite insulators are significantly lighter than their equivalent porcelain counterparts. Polyester films. Polyester films and tapes have been used for the insulation of conductors in the manufacture of motor and transformers. Polyester films are used as slot insulation in the motor manufacturing industry. They are now being used as an insulating material in the sandwich bus for interphase and phase-to-earth insulation. While polyester films are available for a wide range of thermal class of insulation, Class B should be sufficient to meet the specification requirements of Busbar Systems. Mylar is the most commonly used insulation in sandwich busways. It is the trade name for BOPET, biaxially oriented polyethylene terephthalate. The films are available in thickness varying from 12 micrometers, 0.5 mm, to 500 micrometers, 20 mm. Wrapping of polyester films on bus bars is highly automated. The mechanical properties vary for machine direction, MD, and transverse directions, TD. Polyester films are available in rolls of different width with or without an adhesive coat. The insulation required for a sandwich bus, busway, must have the following properties. Good dielectric properties. Low loss angle. Good comparative tracking index. Good thermal conductivity. Chemically stable. Good thermal insulation class. Low moisture absorption. Fire retardant. Flexible for ease of wrapping. Low coefficient of friction. Non-toxic. Stability under thermal cycling, high tensile strength. Long life. Low thermal expansion. Insulating gas SF6 and G3. With the increase in the transmission voltage, there arose a need to make the associated switchgear equipment compact, free from environmental constraints. Man-made sulfur hexafluoride gas with excellent dielectric properties had been synthesized in the early part of the last century and used initially in medium and high voltage circuit breakers and subsequently in gas-insulated switchgear followed by gas-insulated transmission lines. SF6 has found a mention in the Kyoto Protocol and is recognized as a greenhouse gas, but sulfur hexafluoride does not deplete the ozone layer when it is released in the atmosphere. It does not contain chlorine atoms as do the chlorinated fluorocarbon, CFC. The environmental issues arising out of the use of SF6 are its impact and contribution to ozone depletion from byproduct during switching, arc quenching, and corona discharge. Environmental concerns have led to the usage of the gas mix 80% nitrogen plus 20% SF6 and development of green gas for grid G3x3M. Gas-insulated bus, with these insulating medium, are in commercial operation. Thank you. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the Founder Director of Power Gear Limited and Busbar Systems, India, Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.